Let me share screen. Come on, Zoom. Let me do my thing. So, one second. Yeah, so again, I would have expected that synergistic interaction, but you actually see differences in relationship quality when males are not depressed. Down there, that's the down here. This is male depression down here. Let's see, there you go. We can see it. And then you have male relationship quality over here, and then these are the simple slopes of female depression. So as you can see, the more males that are depressed, clearly relationship quality goes down and down and down and down and down. Makes perfect sense. But what I would have expected is either I would guess female depression would have been far more, it would have gone down steeper when female depression was high, but it might actually be that when both people are depressed, there's emotional resonance between the two of them. And we're actually going to talk about that a little today. And there's some theories that suggest your psychological symptoms are communicable, like secondary post-traumatic stress. In that body of research, they talk about compassion fatigue with therapists. So it might be that, yeah, you're both unhappy and you're both depressed, but the female depression no longer has an impact on how you view your relationship. So this is the diagram I was trying to find yesterday, and it was in there all along. So I think I was plotting out last night about what do we have time to cover the random intercept cross lagged actor partner interdependence model, and I think we're going to try to fit it in. That being said, before figuring out time, I was bummed that we potentially not get to it. So what I did was last night is I programmed in the random intercept cross lag panel model with the common fate model instead. And so we can also do that, where rather than looking at individual deviations from themselves, you can look at couple level deviations from the couple average over time. And so we can do really either one. So I'll leave it up to you all. Would you rather do the random intercept actor partner interdependence model where we're parceling out actor and partner effects at the individual level? Or do you want to do it at the dyadic level with a common fate? And we're looking at support and strain using the pair fam data and looking at influence of how support and strain at time 1 is associated with support and strain at time 2, time 3, time 4, time 5, but at the within level. So couples who are higher on support in time 1, are they higher on support at time 2? I'll leave that up to you all. Would you rather do the actor partner one or the common fate one? Yeah, so the actor partner interdependence model, I merge the cross lag model with the random intercept cross lag panel model. And so I'm parceling out the trait levels, and we're using parent-adolescent relationship quality over time. And then we're going to look at within family deviations from your general tendency or your average in relationship quality and see if that predicts changes over time. Or we could do that at the dyadic level.
Both sound great. If I go for the APIM one by a head.
All right, then we can do that. And
then the one you choose will be based on
your
theory.
Yeah, exactly. And the one with the common fate model, you're looking at within couple processes at the dyadic level, but it's within it's kind of looks more like an autoregressive panel model at that point, because you're looking at couple communication and couple relationship quality. And at the actor partner model, you're looking at how I affect myself and my partner. So the analyses are interpreted a little bit differently, but I think it would ultimately depend on your theory. But we'll do the APIM one. I think that one's a little, has got a little more meat on the bone. I've never actually heard of the one at the common fate model. I just went home last night and I was like, okay, can I just program this? And that's how I spent an hour and a half. And so I provide syntax. It's looking a little rough, but I think it's actually really quite interesting. So I said on yesterday morning that the psychological sciences, the behavioral sciences, family science, we do a phenomenally terrible job at parceling out within and between person effects. So if you look at like substance abuse research, we tend to find, if you use just like a cross-lagged panel model, those who are higher on anxiety tend to use more substances. They tend to drink more, all right? Sorry, my voice is a little sore from talking so much yesterday, so I'm got cough drops in. And so you see, you know, time one, and then a year later, time two, I have more substance use, so I'm higher on anxiety. But if you look at within a person, the more anxious they are, the less on day one, the less they drink later that day on day one. It's because anxiety prevents you from going into situations in which you would drink, right? And this is going to be especially true for teenagers. So if you do a panel model, you'd see that teenagers, mental health predicts a lot later substance use. That's a big risk factor. But if you look at like within days, on days that they are more anxious than they usually are, they actually drink less because again, they don't put themselves in those situations. So and that can, I think to me, it's a big problem because we're smushing those effects together. And a lot of the times those effects are going to have opposite signs. So it's not that they're going to be, you know, they're going in the same direction. And you're just you're not able to parse it apart. A lot of times they're going to go in completely opposite directions. All right. And so, and this is a big problem in dyadic research. I've never really seen, I will see John Paul Lorenzo and Niall Balger. They do a lot of really good work with intensive longitudinal data. I'm actually doing a workshop with them in about a month. But it's all in a multi-level modeling context. So multi-level modeling, I think it's great, especially when you have 5 and 10 and 15 time points. SEM taps out. It can't handle that type of growth, those types of intensive longitudinal designs. That's changing with dynamic structural equation modeling. But MLM does a great job. But you can't estimate lagged effects. You can do lagged effects in the residuals. You can have, you know, your residuals at time one predicting your covariating with the residuals in time two in multi-level modeling. You know, if you're a SAS person, there's like 20 different error structures that you can incorporate, but you can't actually look among your predictors those lagged effects. All right. And so again, that's one of the benefits of structural equation modeling. And so I'm going to talk about the random intercept cross lagged panel model, introduce the basic concepts of that. This is where I'm going to be skipping quite a few slides because there's a lot of equations in this one. But I want to just share with you some of the basic ideas, and then I'll talk about the cross lagged APIM, and then we'll move into M+. So the cross lagged panel model is probably familiar to, I'm guessing, just about everyone. It's essentially my scores you have two variables within a person, and I have like drinking and PTSD, and I have time 1, time 2, time 3, time 4, and I just look at the autoregressive effects. So PTSD on PTSD at time 2, and PTSD at time 2, predicting PTSD at time 3. And then you have the cross lagged effects, my drinking and predicting PTSD, and then my PTSD predicting my drinking. All right, fairly basic. I'd say the most basic longitudinal model you can create. And it kind of looks a little bit like this. Right here, I only have 2 waves, but your x's that's supposed that's right. Okay, so you have your x predicting your y and your x2 predicting your y, and then there's a cross-lagged effect. Oops. Like the APIM, it has perfect model data fit. So I said yesterday, if you are familiar with the cross-leg panel model, the baseline APIM is identical visually and analytically. The interpretation of the past changed a little bit, but we have a perfectly identified model. We have 14 pieces of information available to us, and we're estimating 14 different things, right? And again, this is my beef with multi-level modeling. I have no idea whether or not my cross-leg panel model is a good model or not. No idea. And so what we try to do in the social sciences is the randomization's hard, and we do mostly passive observational designs. We try to establish causality. And so we can use a bunch of different ways of data and see how stable the constructs are over time. And I will say these slides are not mine. These are from Danny Osborne in Australia, and he is one of the leaders in the random intercept cross lagged panel model. Him and Alan Hamaker and Jerome Mulder are some of the big names in this. So you look at the stability of our effects over time. And then we can look at, is there a bidirectional relationship, right? We can look at, does construct 1 predict construct 2 over time? Is there a reciprocal relationship, right? Or, and for this might be familiar, is there Granger causality? So Granger causality essentially is the idea that one of those effects, one of those cross-lagged effect, is going to be significantly stronger over time. So we can say that effect is causing the other variable. So in our substance use example, let's say it's going to be my PTSD is causing my substance use at PTSD at time 1 is predicting substance use at time 2. And then PTSD at time 2 is predicting substance use at time 3. And we're seeing that effect over and over and over and over again. Even though we can't manipulate anything, we can begin to say maybe there's a causal relationship, potentially. And that's what's called Granger causality. And so the random intercept or the cross-leg panel model does a really nice job at kind of establishing temporal precedence. That's one of the benefits of this model. It can look at mutual influence of within-person constructs, right? My PTSD to my drinking behavior. You can look at forgiveness and marital quality. You can look at all of these wonderful things, right? And it's limited though, because every cross-leg panel model only has one reporter. All right, so we're already missing that whole dyadic component. So again, keep that in mind. Oops. So the pros, relatively few waves of data. Technically, you only need 2. It accounts for stability of the constructs over time, and those stability effects tend to be 0.4, 0.5, 0.6, 0.7. You know, I was just looking at this, doing a panel model with BMI, and the stability effects are like 0.85 over a 10-year period, which I actually thought that seemed a little high, but you know, it is what it is. And so those effects can be really, really pronounced. You can use one variable to predict change in another. And don't start throwing things at me of what change means, okay? People have been yelling at each other about what change actually means over time for decades. I'm a belief that if you have 2 time points, you are assessing change, right? And you have other people who are say that's not change. To me, it's change. And then once you have 3 time points, that's rates of change. So to me, if you have 2 time points, you're assessing change because you're using a change score, or time 1 time 2 minus time 1, or you're using residualized change, which is what we're predicting here. So change is built into those effects. So in my eyes, I'm going to use the word change, even if we have 2 waves of data, but know that there's people who don't believe that. You need at least 3 waves, and you need to do like growth curve modeling or something to that effect.
Just out of curiosity,
Yep.
what's the argument?
I don't know. I don't understand it. I really don't.
Yeah, that's fair.
I mean, I do mostly longitudinal research. I think probably 60 to 70% of my studies are longitudinal, and I use change. And without a doubt, every time I get a reviewer saying this isn't change, I'm like, all right. And sometimes I'll fight with them, and sometimes I'll just be like, I'm just going to change it.
The issue is you're getting rates of change.
I think that makes sense to me. I don't understand that argument, but yeah, I think you're exactly right. I think it would be people want to see rates of change. And by the way, this is a aside, using covariates to predict like rates of change in growth curve modeling, there are a lot of biases in there, like a lot of biases. So you got to be really careful. There's a paper that just came out, within the last year or two. Ethan McCormick and a few others, they talked about it's like alpha change, beta change, and gamma change, or something like that. So there's a lot of problems there too. All right. Anyways, back to keeping me focused. The cons of the traditional panel model. We test models that are just identified. This is especially true because we don't use latent variables all that much. It yields biased cross-lagged effects when there is a stable trait-like component to it. And that's kind of where I'm going with this. What we're going to do on the random intercept models, we're going to pull out that trait-like component. And it confounds between person stability of within person change. So like going back to this model, can you really say that, that a person has changed here? Can you regression coefficient of 0.45, is that actually capturing change of some kind? And to me, I kind of struggle with that idea. I'm like, I don't think so. Maybe a little bit. And so what we're really going to do is we're going to begin to shift into the really capturing the idea of change. So here's an expanded version of the panel model. And here are the equations. So I'm not going to dive too deep into them, but in the cross-lagged panel model, you generally assume that your time 1 variables have a 0 effect on your time 3 variables, and it's presumed that the effect is mediated through time 2. All right. But I have a couple studies, especially in parent-adolescent relationship quality, where time 1 predicts time 3 above and beyond time 2. Do you know what that tells me? That there's a trait-like component that I'm not modeling. There's essentially you create a covariance, but what a covariance is nothing more than an unmeasured cause. That's what a covariance is. There's an unmeasured cause that's linking those two variables that's not in your model. I'm a big fan of the cross-lagged actor-partner interdependence model, looking at, again, stability and change within dyads over time. And it's modeled in the exact same way as a cross-lagged panel model. And now you will have 4 degrees of freedom. All right. If your time 1 does not predict your time 3. Right? And of course, if you're using latent variables and you're using longitudinal data, you need to test measurement invariance unequivocally and without excuse. All right. And so if you're using latent variables, all you need is configural invariance, which is your factor structure needs to be the same, or metric invariance, which is your covariances need to be the same. You do not need scalar or strict in order to model latent variable, like the associations among latent variables. You should probably want it. We want measures, because if you don't have scalar, then you can't do any growth modeling with that construct, okay? But technically it's not needed. You only need metric invariance. And you can even get away with, let's say you're studying like kids from like 0 to 18. Like what is aggression to a 3-year-old versus what is an aggression to a 9-year-old versus an 18-year-old is going to vary a lot. So good luck trying to pin down a measure that assesses everything effectively. You can actually pin down, if you have one indicator that is invariant across time, you can use that as to set the scale of your latent variable, and then allow all the other indicators of aggression to vary over time. And you can actually then use structural equation modeling without having all of your items having to be invariant. So there are ways to get around things like that. So again, here's my study. This is the one I referenced yesterday. Again, this is a cross-lagged actor-partner interdependence model where I have parent and adolescent reports of relationship quality at 12, 14, and 16, and I'm testing that as a mediator between post-traumatic stress symptoms at 12 and 16. All right. And so we've already outlined about how that's limited. That's just, again, a dyadic application to the cross-lagged panel model. So what we're going to do is we are going to try to estimate those within person changes. And so there have been numerous models developed over the past, 15, 20 years, 25 years now, that try to get at within person change. So you have the alt model. This was developed by Ken Ballin and Patrick Curran. I think it was more Ballin. This was in the, late 90s, early 2000s, somewhere in there. I actually don't see it used all that much. I think we have a lot of better approaches now. You have the latent state trait model, which is Dave Kenny, again, the father of dyadic analysis and author of this book, the book that I'm going to be requiring for my class next semester. We now have dynamic structural equation modeling, which is, again, I think yesterday I mentioned, it's a merging of time series, multi-level modeling, SEM. And then we have the random intercept cross-lagged panel model, which we are going to talk about today. And so what the random intercept cross-lagged panel model will give us, I can pull out that trait level stable effect over the study period. All right. And then what I have is then within person deviations from their average. So on average, I could be, a fairly optimistic person. But, there might be changes in my optimism based on life circumstances or relationship problems or whatever it is. And with a cross-lagged panel model, you are not getting at those changes. You cannot get at those changes, right? But with a random intercept cross-lagged panel model, you absolutely can. I'm going to quote Lisa Hoffman because I think she has one of my favorite quotes is those between and within are smushed together, right? They're kind of, you can't pull them apart, but the random intercept cross-lagged panel model, you absolutely can. All right, so I'm going to define between person effects and within person effects, because though it took me like 6 years to get it. And I took multi-level modeling twice to try to get it, and I still didn't work. But I think I finally got it down, and I'm still somewhat gaslighting myself into questioning whether or not I actually know it, but we're gonna take a shot at it. So between person effects is what is occurring is comparing all of us together. So when we have a group mean of everyone who's here today, I could be higher than the group mean. You could be one person's going to be lower. A few people can be at the group mean. So that's the unit of analysis. And that's what we're doing in the active partner interdependence model. That's what we're doing in correlation. That's what we're doing in regression. That's what we're doing in SEM. It's all I'm comparing me to you, to you, to you, to you. And that's what moderation is. I mean, it's comparing group level means. All right. But within person analyses and within person effects is I am comparing myself to myself at a previous or future time period. Right. And so I have my dispositional level of optimism. That's the between group, right? And then you have yours, but also my level of optimism is going to fluctuate based on, again, these life circumstances. So we can capture those within person fluctuations, those deviations from my general tendency to be optimistic, right? And that's what within person effects are, right? Just a point, because I hammer theory really hard, is almost every theory that you have is focused on within person effects. I mentioned this yesterday. Family systems theory is family. The ideas of family system theory is that families on average, when mom yells at dad, that elicits this response. No, not really. It wouldn't argue with that proposition, but the core of family systems theory is when mom in this family yells at dad, this is how dad responds, right? And then dad yells at the kids, and then the kid yells at mom. There's a circle of screaming that's going on, right? So that is the core of family systems theory, and that's at the within person level, right? Again, family system theory wouldn't disagree that there are these patterns on average that are consistent across families, but particularly me as a clinician, I really only care about the patterns that are going on within the family that's sitting in front of me, not the family patterns on average. So I kind of get it when clinicians say, how can I use this research in practice when, well, actually, I'll say it a different way. They say this research doesn't apply to the population I work with. I get that all the time. And that's because it's aggregate. It's not looking at individual folks.
When you're doing within, when you're looking at within person effects in a statistical analysis, is it looking at average within person effects across a group of people?
Yeah. It's average. So it's like the way I think about it, like if you do like growth model, like it's average, like let's see if I can say that right. Inter-individual differences and intra-individual change. So it's individual differences in my level of change. So there is still a group component, but now you are looking at your own, essentially your own aspect of change, rather than if it's just at the between level, there is no individual at all in it. So it's still, there's still a component of group comparisons, but again, it's at the individual level. And that's the part of it that I still struggle with. I'm like, that's where I still gaslight myself. I'm like, is this really individual change? Like, but I think that I mean, what I've come with is, okay, if I really want to know what true individual level changes, I'm gonna go do like a time series analysis, right? So, yeah. So this is a visual representation of the smushing, right? So in the cross-lag panel model, you just have between person depression. But in the random intercept cross-lag panel, you still have with between person depression, it's still there. That latent trait is, we can compare all of us. It's still at the between level, but now you have, compared to where I usually am I more or less depressed? All right. So here is kind of a visual representation of within and between within the random intercept cross-lag panel. So here we have, and again, it's not very clear probably. Here is at the very bottom the random intercept is my across the study period, and that's really, really important. I've seen studies that find a random intercept. It's defined by between person differences and their average levels of the construct at over the study period. And they say, oh, there's genetic influences in this random intercept. You cannot make that statement. Okay, this is the trait level mean of the construct over the study period. All right. So if you want to study genetic influences, you got to do like a Chomsky's or Cholesky's decomposition or something like that. So again, this is between person average across the study period on depression. That's going to be our example here. So I can have a score, my score can be 12, your score can be 8, your score can be 5, your score can be 16 or whatever it is. That's our average levels of depression across the entire span of the study. But, and you have to have 3 waves to do this, right? I can, if my score, I forgot what I gave myself, like I'll say I was an 8. At time 1, I could have been a 7. So I'm less depressed than I usually am over the course of the study. At time 2, I could be a 15. I could be way more depressed than I usually am. And at time 3, I could be, perhaps like a 9 or something like that. So there's some part of that's going to be characteristic of my average levels of depression, but then part of that's also going to be indicator of my change as a result of things that are going on in my environment. All right. So that's really what we're capturing. And then we can use these to predict one another at the within person level. If I'm higher than I usually am on depression at time 1, what is my time 2 depression? Am I higher or am I lower? I might be lower for some reason. Perhaps if you're doing like an intervention study, and you're doing a within-person analysis, I might actually be lower on average. Okay. Is the distinction between within and between making sense to everyone? So there's going to be, and these are where I'm going to start doing some skipping. Essentially, they're going to be 3 primary components. You still have your group level mean at every time period, so that doesn't go away. We're just going to kind of ignore it because we don't really care about means in this model for the most part. And SEM in general, we really don't care about means unless we're doing like growth modeling or something. And then you have the trait component, the between person average levels across the study. And then you have the within person component, which is an individual's deviation from their random intercept. So here are all the equations. There's a lot of them. I will, do I want to stop here? All right, so here is the full random intercept cross-lagged panel model, right? And so again, what you see here is you have X and Y, and these are your observed indicators, these X1, X2, X3, Y1, Y2, Y3. Those are the scores in your data, in your SPSS file. So you really only need 6 variables in your SPSS data set to estimate this model, right? And then you have up here at the between level, you have your random intercept, and you can fix the factor loadings to be 1, like I've done here, or you can freely estimate them and constrain them to equality, right? To me, I could go either way. So, and people, and like Todd Little and Danny Osborne, they say constrained to equality. If you talk to Ellen Hammacher, she says, fix it to 1. To me, fixing it to 1 makes more sense, because if we're saying it's a trait-like deviation, then we should fix it to 1, and it's consistent across the study period. If you allow it freely to vary, then I'm not really sure what those factor loadings now mean. I don't really know how to make sense of them. So again, neither one was wrong, and you can test whether or not they're statistically different than one another. So ultimately, it may even be a moot point. And then remember those, I talked about phantom variables yesterday. We're really going to get into that today. These are phantom variables right here. All right. And then you'll see that X1 and Y1 do not have a disturbance term indicated by an arrow, because again, actually, I'll ask you, why don't we have a disturbance term on X1 and Y1, but we do have on Y2 and Y3 and X2 and X3? Why don't we have an error term? What assumptions do we make about our exogenous predictors? Perfect reliability, right? That's why we don't have an error term on our X1, because it's an exogenous predictor. Okay? It has a variance, but it doesn't have a residual variance. And you can do the random intercept cross-lagged panel model with 10 or 12 ways of data, depending on what you're doing. And you can incorporate observed variables, or in this diagram, these observed ones right here, they could be latent. And so you can disattenuate measurement error. And so that's what I did last night, is my common fate variables, they're latent. And so measurement error isn't as much of a concern. And so it's entirely possible to have, exceptionally complex models that provide you really precise, accurate estimates. All right. So here's some interpretations of them in comparing the random intercept to the traditional cross-lagged panel model. And so I want you to internalize the autoregressive and cross-lagged effects. But in a minute, I'm going to switch those to actor and partner effects. All right. And essentially, they're going to be the exact same thing. All right. They're interpreted the same way. There's just slight distinctions that rather than talking about within an individual, we're talking about within a dyad. So in the random intercept cross-lagged panel model, there's the autoregressive effects. The within-person effects at time 1 predicting the within-person effects at time 2 are interpreted as the tendency for departures from a trait-like mean to carry over into a later assessment. All right, often referred to as inertia. It's a deviation from a person's trait level of whatever your construct is, persists as a deviation from their trait level of that same construct at a later time. Right? And then the cross-lagged effect is the extent to which a deviation from a person's average score on that construct predicts deviation from their average score on the other construct being modeled. So from an actor effect perspective, it's a person's deviation from their mean affecting their own future deviation from their mean. And from a partner effect perspective, it's a person's deviation from their mean, predicting their partner's deviation from their mean, from their average across the study period. And by the way, Jerome Mulder has a phenomenal webpage with M+ code, with Lavon code, with extensions. You can do multiple group stuff with this. Phenomenal. I think it's a reference in here. All right, so we have interpretation. Okay. So let's just go into M+. Instead of me going through a bunch of slides, let's go into M+. And so let's see where. Here it is. Here's the data file. It'll be RI loadings constrained to equality. We'll use that. We'll use that data file. See if I can find it. All right, there we go. All right. And I ran this in the demo version, so it should work. You have way more than 6 variables in here, but only 6 of them are going into your model. And so in this analysis, we have adolescent reports of relationship quality measured at 3 time points with 7 items each. And then we have parents' reports of relationship quality measured at those same 3 time points when adolescents were 12, 14, and 16 with those same 7 items. They're mirroring one another. All right. So we're actually going to have to create composites. And so we're going to go down first into the define command. All right. And the reason we are doing composites here is I did a measurement invariance, longitudinal across person, and these were the invariant items. All right. So you want to add in PRQ is parents' reports of relationship quality. Then you want to add item 1, 5, 6, and 7 together. So this is item 1 at age 12. That's how this is coded. This is item 5 at wave 12. And this is item 6 at wave 12, so on and so forth. All right. So enter in the create these composite variables. And I'll give you, and that can take a minute, so I'll give you all a minute. While people are doing that, any questions? I want to give people enough time. And essentially this, I mean, don't do this, but I'm going to tell you to do this. What I do is I just, since it's the same across wave, I copy and paste, and I change this to 18, and then you can just change that. That's how I do it. That's those little shortcut that I take that invariably leads to syntax errors every once. And then in the analysis command, again, we're using robust maximum likelihood. Again, this is one of the cases where you should probably, I would advocate you probably use robust, because this model is getting exceedingly complex. And so what you're actually going to notice at the within portion of your model, your standard errors are going to be really high. And so that's a normal part of the model. It doesn't mean your model is running incorrectly. But we're getting complex. And then this is absolutely essential. So we want to do model equals no code. So M+ by default will automatically covaries the residuals on your independent variables. And we want to override that default here. All right. We don't want M plus to automatically do that. So we tell it no cove, and that means we have to specify all the residual correlations ourselves, right? And then we have, and this is where it begins to get tricky. So we have our latent variable here. So we're first going to specify our, oops, that's actually backwards. This is ADO. This is parent. So you do the by statement. So again, we're constraining it to equality. So we have a by statement, and then again, M plus by default fixes that first factor loading and the mean of that factor, the first factor loading to be 1 and the mean of that intercept of that item to be 0, right? We want to override that default, right? We want to freely estimate all of the factor loadings, but we are going to constrain them to equality using the parameter labels that we talked about yesterday. And it can, I just use Z1. It can be really whatever label you want to throw in there. And so we restrict 12, 14, and 16 to be equal for parent. And then we're going to do the same thing for adolescent, and then you give it a different value label, right? Like if you had, this is parent adolescent, so I think there's a lot of developmental changes that are happening for parent, or less so for parents, but also for adolescents. And so I constrain them to be different. If you have like couples, for example, you might even constrain these to be equal. You could make all of the parameter labels Z1, right? And then for those of you who are familiar with confirmatory factor analysis, when you free the loading, you have to pin down that latent variable in some way, shape, and form. And you can use either effects coding or the standardized method. And what I'm doing is I'm using the standardized method. So that means I'm fixing the mean of the latent variable to be 0, and I'm fixing the variance and the standard deviation to be 1. So that's this right here. I'm fixing the variance to be 1, and I'm fixing the mean to be 0. So don't forget those brackets on the mean, right? Oops. And then we're going to covary those factors, because my belief would be is, the higher adolescents are in relationship quality with their moms, the higher the moms are going to be on their relationship quality with their adolescents on average across people. All right.
On the RI adolescent, that is 0, 1, or the character? Yeah, next to, yeah.
This,
Next to the pocket.
so that's at 0. Yeah, it's the at symbol. Yep. Yeah, at symbol is a way to constrain parameters in M+. Oh yeah, yeah, good. Yeah, that should be the same. And then ADOL, yeah. So once you have this specified, this is essentially the measurement portion of the model. Now we're going to go create these phantom variables. All right, so that's this within person effects code down here. These are, all right. So phantom variables, generally they're specified by they're going to be a single indicator latent factor, where the observed variable for adolescent 12 is going to be the only indicator on that latent variable. And you are going to restrict that factor loading from that latent variable to be 1. And you're going to do that for each observed variable that we have in our model here. And again, this is helping pin down those latent factors. And if we were doing like growth curve modeling, we would also be doing something with the means, but since we're not as worried about the mean structure in this model, we don't really have to worry about it a whole lot. So you have these with the adolescent, these phantom variables, and then you do the exact same thing with this, and you can name these whatever you want. I normally call them within, and then provide a brief summary of the variable.
Can you provide, what's the definition of fact?
So there's going to be slides on it.
And that's a later.
But it's essentially it helps us with when models it's one of those things where I know it when I see it, but it's hard to describe.
Okay.
Essentially it helps with when there's a lot of constraints in a model, it helps I don't want to call it like a shock absorber, but it allows us to estimate different types of effects. So I will, that's a very bad definition for right now. We'll get to the slides and we'll see if I can explain it any better, but it's honestly, I wouldn't worry about the formal definition of a phantom variable. I honestly don't think it's all that relevant. At least right now. And honestly, I don't think I've ever seen like a formal definition either. I think people like talk about phantom variables and they don't really define it, which is like a hallmark of statistics and why people hate learning statistics. Yeah, right. Yeah, exactly. Yeah. And we can use delta to represent 10,000 different things depending on the model that you're using. You fail to reject non-invariance over time. Well, what does that mean, right? All right, so these are the phantom variables. And then what we're going to do is we're going to create the lagged effects, the actor and the partner effects within that within portion of the model, right? And so, and there's actually there's newer syntax where you can do an M plus, it's called P on. Seriously, it's called P and then on. And you can do this automatically, but again, sometimes models are finicky, especially when you're doing really complex stuff like this, and you have to constrain some of all the actor effects to be equal over time in order to get the model to converge, or sometimes you have to constrain the partner effects to be the same in order to get your model to converge. So I do it this way, so if I need to throw in value labels, I can, and I don't have to redo my syntax. And then, so here you have your within person. This is adolescent at time 2, and it's being predicted by adolescent at time 1 and predicted by mom at time 1, right? And then you have the exact same thing here. You see I have a value label there. Mom at time 2 being predicted by adolescent and mom at time 1. I'll actually fix this real quick. And this is actual data from a manuscript that I'm about to submit to an adolescent journal. And then we have, whoops. And the reason it's such a mess is I have like 10,000 data files in there, each with different constraints and stuff like that. So it gets a little messy. So after you've done the lagged effects, in order for your model to identify, you have to fix measurement error or variance, I guess you could call it, to 0 on your observed indicators. So we have our observed indicators up here, ARQ 12, 14, 16, need to set all of that to be 0. So essentially what we're doing is we're telling the model to push that information that is at the observed indicator level in terms of variance, we're pushing it down into the phantom variables. And then the last thing you do is you covary your within person effects at the time period. And we're gonna be doing more with phantom variables this afternoon when we talk about the common weight model with individual and dyadic parameters. And you probably want in your output, you probably want to add tech 4. That wasn't necessarily in there, but that's variance covariance information for your latent variables. So if we get potential problems in estimation, that's one of the places we'll go and look to see where there's problems. If there's a Hayward case or something like that. A negative variance, in other words. Any questions about the syntax thus far? All right, so I'm actually going to go ahead and run it. Hopefully it works since I've made some. Oh, there it is. Thank you. Yeah. Oh, let's see what happens. An environmental with statement. Oh, I think it's the same problem.
Yeah.
I think all of the rest are eyes. Oh, there's one. Let's see if that works. All right, there it is. So I'll keep the syntax up here in case there's some people still working. All right, moving along. So we have 305 observations, 6 dependent variables. All right, so scrolling down. All right, so we got a warning message. Latent variable size not positive definite. All right, so that's something we would need to think about. But what we'll do is we'll go through and we'll interpret the effects as if it's legitimate. I think my sample had 479, so it might be it could be a sample size issue. But I gave you a reduced version of the sample. So we'll scroll down to the standardized effects. And the random intercept cross lagged APIM model, I think by definition has 1 degree of freedom. I believe that's going to be fairly consistent. And so your model's probably almost always going to fit really, really well. All right. Because it can't not fit well because all the things you can estimate, you are estimating. Okay. So I can already tell you where the problem is. There's something going goofy on right there. It might be a missing data problem. It might be something else. So you'd want to look at these factor loadings, because I guarantee you that's where the problem is right there, and right there. And so here is where our within statements are, our within statements are. These are the things that we really care about. It's going to be these parameters right here. Everything else is we're kind of just checking to make sure things go according to plan. So within adolescence, that means adolescence at adolescent deviations at time 1 have a 1 standard deviation unit and increase in those deviations. It results in a 0.15 standard deviation increase in adolescent deviations at time 2, and it's positive, but it's not significant, right? It's not significant. Let's go down to a significant one or borderline significant one. So the more one standard deviation increase in mom's deviations from her mean in parent-adolescent relationship quality at time 2 predict a 0.29 decrease in adolescent deviations at time 3. So the higher mom is on her relationship quality when the adolescents were 14, the adolescents report lower relationship quality at 16. Right. And I think some of these dynamics, I wouldn't fully trust these, some of these estimates, and I'll go through and I'll show you what I actually wrote up in the paper because it says slightly different. Is that if we look at just the cross-lagged panel model, we'll see lots of stability, right? We'll see those stability effects of 0.4, 0.5, 0.6. But if you ask any parent when they have a teenager, is your relationship quality the same before teenage years versus during teenage years? The parents say, no, we fight more, they're whiny, they complain, they're needy, they're hormonal, what all of us were as teenagers. And so how does that make sense how do we reconcile those types of findings and those types of narratives with, okay, at time 1 that predicts time 2 relationship quality at 0.50, the beta weight at 0.50. It doesn't make sense, right? And so that's what this gives us. That's what this part of this model gives us. It allows us to detect those potential declines in mom's reports of relationship quality, especially at the onset of adolescence, right? And so that's why I actually chose these data is because I have 12, which is right around when puberty kicks in, maybe a little later for some than others. But that's the onset of adolescence when kids start pulling for, I want more independence. I want to make my own decisions. You're not going to tell me what time to go to bed, that type of stuff. And so we can capture that at the within person level. All right. Any questions about the model or about the random intercept cross-lagged panel model, about how it's different than the panel model and how to interpret the actor and partner effects at the within-dyad level? Okay. Then we will duck out of M+, and what we will do is I'll actually walk you through what I actually found in the paper. So here's what we found in the paper. Oops, let me put that in full screen. So we found that there's, again, fairly strong stability effects especially among adolescents. And I think those are significantly stronger, significantly higher than mom's stability effects over time. And that adolescents actually demonstrate a partner effect. So the higher adolescents are on average across groups, that predicts mom being higher at 2 years later, controlling for mom's time 1, right? And then we have a partner effect here where, excuse me, right here, that 0.19. So, the higher moms are at 14 is associated with adolescents being higher when they're 16, controlling for adolescents reports at 14, right? So again, it makes intuitive sense. Like there's a bidirectional effect and we don't see the partner effects going the other way. But when we throw the random intercept cross-lagged panel model into it, we find that there's no correlation between parent and adolescent deviations from relationship quality. Those are completely unrelated. Think about that. Mom and adolescent deviations from how they traditionally and on average view their relationship, those are unrelated to one another. They're completely independent. And what we see here is adolescents who are, again, on average, who are higher than they usually are in relationship quality at time 1 are higher than they usually are in relationship quality at time 2. Right, that makes sense, right? That those stability effects haven't really changed. They've gone down in magnitude because we've pulled out that stability, but they're still very much significant. But look here. Look at that mom's effect. This is the decline that I was talking about that I would theoretically expect. that is completely indetectable in the panel model. So this is where moms who are higher than they usually are at time, higher than their average mean across the study, at time one, it's going to predict being lower than they usually are at time two. It's going to predict deviations in their mean. And that's the firestorm that is adolescence, right? That's what I think we're capturing here. It's not significant, but it just, one, it goes to show that there's an opposite sign here. And so that tells me we really need to disaggregate these within and between effects. And we see there are no partner effects. Why wouldn't we expect, according to family systems theory, wouldn't we expect partner effects? Why wouldn't we have partner effects here?
Kind of understand your review where we expect adolescents from a human development perspective to be gaining more like independence,
Sure.
trying to spend more time and energy with friends and stuff like that. And so
Sure.
being attenuated kind of thing going on.
Okay. I would agree with that. My argument is, if we're thinking about family systems theory, and I think we also use attachment theory in the paper, is the norms in the relationship have been established prior to adolescence. How parents and adolescents communicate with one another, how they interact, how they are just in relationship with one another, that's been established in those first 12 years that are not available in our study, right? And so we're not going to expect a whole lot of major influential changes. Yeah, there's going to be conflict. Yeah, there's going to be communication, but that doesn't change how they typically view one another, right? And so that's kind of those are my thought processes. But again, think about, these are 2-year lags. What if you did the study 1 month, 3 months, 6 months? 6 month, 1 year, 1.5 years, right? The time lag, that's another thing we are god awful at. If I could change one thing in the social sciences is, can we develop a theoretical rationale for time between waves and longitudinal data? We might get very different. If we do this on a day-to-day, like a daily diary study, survey parents and kids on 6 consecutive days to see what happens, right? So again, I think this model just gives us so much more. I'm all in favor of abandoning the panel model if you have 3 waves of data, or at least present both. The very minimum is my perspective, because again, the panel model isn't like bad. It's not, but it lumps things together that shouldn't be lumped together, and it's just creating a whole lot of bias. So what I did in the paper is we reported both, and we talked about what are the implications for the between family and the within family analysis. And what you can do is some FAQs about the random intercept cross lagged actor partner interdependence model. I've only seen this published once. I think I'm going to be the second study ever to use this model. So it's not all that common. It's not all that out there. And so I like to talk about some of the questions that we might have. You can incorporate predictors into this model. You can predict the random intercept, and you can predict the within person component. You can predict what are the reasons people might deviate from their general tendency to be satisfied in their relationship with their mom or their adolescent. I think that's phenomenally informative. To me, that's where clinicians can actually have something to use, right? And so you can have distal outcomes. You can have with the within person components predict a distal outcome. You can have the random intercepts predict a distal outcome. You can do a whole lot of really creative stuff with the model. Can you incorporate growth into this? Sure can. That's what I'm working on. All right. That's the dyadic growth curve of structured residuals. Right. And then again, this is the dyadic growth curve of structured residuals that you've already seen. Okay. So these are just the report, going over the findings that are actually in the study. And as you can see, our standardized loadings actually aren't that aren't that impressive. And so that tells us that there's a lot of variation that's happening at the within level. Right? And this is a slide I added last night. You can test mediation at the within person level doing this. But you're going to need a big old sample size. And you can do this at the within person level really quite easily, but you can actually test. You would actually need think about the APIM EM that we went over yesterday. We just create 6 random intercepts for each of those variables, and you can test it in a cross-lag panel model at the within person level and actually test mediation at the within person level. Now, don't tell me that's not freaking cool. And there's some data sets that can support this, like the PairFam data out of Germany. I don't know, I think there's 8 or 9 waves, dyadic, longitudinal, and actually it's triadic even. I think they have kids too. And they have, I don't know, 8,000 people or 9,000 people. So we can run, there are data sets out there that can support these conclusions. And that's just, I think to me, it's just waiting to be mined. If I had the time, that's where I would absolutely be going, is getting more familiar with PairFam so I could run these with in-person mediational analyses.
It's okay.
PairFam. It's in the syllabus of the Dyadic class I'll be teaching, and 2 the seminar class I taught. I think it should be in there. It was one of the methods articles that we read that first week. Yep. And here are the resources for the data set. Or not for the data set, for the random intercept cross lag panel model and the APIM. And we can also Thomas Loy's, he extended the APIM to categorical outcomes as well. So we can also do that. All right, so this is a section I'm completely skipping. This goes into latent variables and multivariate APIMs. Just more advanced. All right. So this is embarrassing, and we're actually going to probably take a break before we get started. I chose that GIF because there's a song that was related to Common Fate, and that's from the music video, and I don't remember the name of the frickin' song. It's driving me nuts. We'll take a break now until 10:30, 17 minutes, and then we'll come back and we'll start Common Fate models. I think it is. I think so. I don't know. That might be how I spend my break. Is figuring out what song this is. Because there's a rationale. I was like, I found the song, I found the GIF that was perfect, and I can't remember what it was. All right, I'm going to pause back. And now we are going to start into the Common Fate model. So this is a model that tends to hurt your head a little bit more when it comes to just thinking about, because unless you're a seasoned multi-level modeler, I found it, at least I'll speak for myself, hard to conceptualize what a level 2 variable is, and that's really what the Common Fate model is getting at. So the Common Fate and the APIM, I'm going to say this probably 3 or 4 times, they answer a completely different set of questions, and you need them both, right? Especially if you're thinking like a family systems theory perspective, you need both, because some of the theoretical principles in family systems theory are about mutual influence. I affect you, you affect me. But also some of the ideas of family systems theory is there is shared belief among family members. APIM doesn't even come close to being able to measure that, right? It's all about the influence. So you need both Common Fate and APIM to fully test the propositions of many of our theories. Attachment theory would probably be the exact same way, right? And so the APIM, again, is focused on mutual influence at the person level. Again, I showed you that diagram where the APIM is nothing but individuals and how they influence one another, which means, is it really a dyadic model? I'm like, kind of, maybe a little bit, not really. But the Common Fate model at its core is a dyadic model. It is the dyadic model, in my opinion. And so in the APIM, we account for the non-interdependence through mutual influence of the partner effects and the residual correlations between partner one and partner two. But in common fate, we have to do this within an SEM. We cannot do this within a multi-level model framework, to the best of my knowledge. You're counting for non-independence by having a dyad level, a level 2 latent variable that is causally related to each member's individual reports of that construct. So if we have communication as a level 2 variable, when we have partner A and partner B report on their own communication styles, we are fundamentally assuming that each person's reports of their communication styles is causally related to that dyad level or that relationship level construct up top.
It's similar to the way that you can have multiple levels of latent variables in kind of classic SEM, where there's like a latent variable that can predict other latent variables, but in this case, the higher order one is at the group level.
Kind of, you can view it that way. I think the only potential, I don't want to say it's not even a problem, is the indicators for common fate are almost always observed. And so if you think about higher order latent variables, I think there's gonna be confusion that's created, but I think it's not a bad way to actually conceptualize it. So yes, so I'd say if it works for you, then yes. It doesn't work for me.
Sure.
In the common fate model, dyad numbers are presumed to be interdependent on one another because of something that is shared between the dyads. So shared attitude, shared communication, shared dyadic coping, shared beliefs, shared whatever it is. Okay? And so this is what makes the common fate model a little bit more restrictive than the APIM. Because again, if the emphasis is on dyad level processes, shared processes, you can't really have individual level variables in there, can you? Because our individual level variables shared? By definition, no. And so that's one of the reasons that the common fate is a little bit more restrictive. So here's just, again, a visual representation, the same slide as 300 slides ago, right? These are the forms of the interdependence. And here is how the common fate model conceptualizes interdependence. It's through the shared covariation that is captured within this latent construct. All right. So again, in the APIM, the individual is the unit of analysis, and the common fate, it is the dyad that is the unit of analysis. So this has been around for, I don't know, almost 40 years now. It hasn't gained a whole lot of traction. One, because, well, back when it first came out, SEM was still in its early Lizrel days, and Lizrel was great for the time, but as we look back on it, it's just really severely limited. The APIM is just so easy to understand, I think people default to the APIM because it's kind of a substitute for thinking, because it's really easy to think about and really easy to conceptualize, and you can kind of retroactively change your theory to fit like an APIM framework. But essentially, it's been around since '85, and the purpose was to partial out individual level effects from group level effects. So you can actually have a common fate variable that is indicated by mom, dad, and child. It doesn't have to be just mom and dad or a parent and child. It can be any number of different people. You can have a triadic common fate variable for sure. So again, the common fate does really, really well in capturing that idea of what is shared between family members. You can't just look at person one and person two in order to fully understand the complexity of the family. The whole is greater than the sum of its parts. 1 + 1 = 3. That's what your common fate variable is giving you. So measurement. So we talked a lot about measurements yesterday morning. And so in the common fate model, the reason we had that extensive discussion is to set up what we're going to talk about today at the common fate level. right? So with common fate variables, you can only use measures that are dyadic level, that are dyad level. So those individual level effects, can't use them. Those partner referential items, can't. I think there's an argument to be made, because if you and your partner are talking about how you perceive each other, there's probably something that's common among them. So I think, to me, I'm a little on it. And what I have found with those types of items is they load decently well, but it tends to be below the threshold of what is recommended of 0.70. So I'll talk a little bit more about that here in a few minutes. And with measurement, just because you have variables that are highly correlated with one another does not necessarily mean there's a theoretical rationale that the covariation is explained by a dyadic level process. Okay? So just because you have depression correlating at 0.60 between husbands and wives doesn't mean that there's a shared dyadic process that is causally indicating each person's measure of depression, right? And so within the common fate, you have to report on the same variables and it has to be dyadic. With APIM, you actually don't have to have the same variables. I think it's kind of a weak research question if you don't, but you don't theoretically have to. But in the common fate, you absolutely do. So it's essentially, to be more statistical about it, and maybe perhaps be a little bit more concrete, it's shared variance in the form of a latent variable in one construct predicting shared variance of a latent variable in a second construct. That is the baseline common fate model. So I said a minute ago, you can't really do this in a multi-level model. Actually, why can't I just take a sum score or a dyadic average? Why I have communication for partner 1, communication for partner 2? Why can't I just sum those up and divide by 2? And that be good enough for a multi-level model in the common fate?
The one theory, at least the way you have two different people communication, I don't think that's not necessarily the same thing as talking about a couple level process. You mean if you do like a classic Sue Johnson pursuer distance, that's even like one person's pursuing and the other person's distancing. That's not the shared system. The shared system is like what that defines them as a couple. Those are different concepts.
Okay. So how connect that to the dyadic average for me? How would so to me, when I hear pursuer distance, I see two different scales kind of. So connect that to the
I mean, again, I could be just barking up the wrong tree here, but at least the way so if you have so if you take something, let's say we just use like empathic listening as a scale or something like that.
Okay.
I could have my empathic listening and your empathic listening.
Sure.
And you could, if you average those together, that's just giving you what our average individually kind of spaced out empathic listening is.
Okay.
It's an average between us as a group, but not necessarily at a conceptual level, like there's some shared theoretical underpinning dyadic level of empathy that's predicting both of our stuff. There could be like a latent variable of like, I don't know, a characteristic of our relationship as being understanding that predicts my empathy and your empathy, but that's different than my empathy and your empathy measured on.
Okay. So essentially what you're boiling down to is a misspecified model and incongruence between theory and how we measure things. Okay, absolutely. What are some other potential problems? That is one. Why can't we just create a mean score of dyadic? Let's do dyadic coping. Those 5 items that all about we. Why can't we just create a dyadic mean? What are we doing by creating a dyadic mean? Okay. Okay. So the between couple, the same score can have very different implications across different couples. Absolutely, right? I think that's absolutely a big problem. So so I think those are ones I probably hadn't actually thought of. But to me, what you're assuming by creating a sum score is you're assuming all the variances at the dyad level. 100% of that variance is up there by creating a mean score of a dyadic mean. And so that goes back to what I was talking about yesterday. That's codependence. And we have to be able to make room for the individual within the context of dyadic research. And so, because again, think back to the imposition of a measurement model is you're assuming by creating a dyadic mean, your factor score will be standardized, and your factor loadings will each be 1, right? And so you're saying they contribute equally and their residuals are identical. When the reality is that might not be true. You are fundamentally assuming that partners are identical in nature. That's just not the case. There's no room for the individual in a dyadic mean score. All right. There's also big problems with measurement error. But in the common fate model, so again, just going back, what these residuals give us, that allows the individual to be entered into the model in some way, shape, or form. Right? Because this is essentially what this residual is it's everything that is not related to the dyad level process, right? So that's really why we need structural equation modeling. Is that making sense? Okay. Okay. So here is kind of again more of a pictorial representation of the common fate model, where we have this dyad level process that's occurring where we have 2 latent variables, and then they're predicted by a regression coefficient. And then we have our unstandardized factor loadings. They're going to be fixed to 1. We'll talk about that here in a little bit on why we do that, but essentially it's for statistical identification and as well as theoretical reasons. And then we have our individual level down below, right? And we have these covariances here because these are within person reports. So this is X1 and Y1 are reported by the same person, and we want to account for that reporter bias to that reporter's perspective. So one of the assumptions that we're making by implementing the common fate model is that the dyad members are similar to each other because of the interdependence, right? And so that similarity is going to be due to a characteristic of the relationship between those people themselves, or something common that they are going through, or a common situation in which they are embedded in, right? And so if you have, like, let's say you have dyadic coping, but it's only correlated at 0.3, that's probably not going to be a common fate variable. Those correlations are a little too low. There's not a whole lot shared, right? So if they're correlated at 0.3, anyone know how much variance is shared? Point 0.3 times 0.3, 9%. That's not a whole lot of variance occurring at level 2. You might want to model that. That might be non-trivial variance, because if you just go to an APIM, that variance is getting absorbed other places in the model, and so that might not be great. But it might not mean that there's a whole lot happening at level 2. So that's where you got to kind of make a really informed decision about how you're actually going to account for that 9% of variance if there's low correlations. Okay. And so we need to really begin to think about what are dyadic level processes and dyadic level measures that we can do. And so don't measure depression, measure family emotional climate. And hands off, I'm creating that scale so it's mine. Okay, hands off, because that scale doesn't exist. I don't know how, it doesn't exist. So rather than trait mindfulness, we're going to go into relationship mindfulness. Right? We can report on something, again, something that's shared between dyad members that isn't characteristic of the relationship. A neighborhood, for example, right? So you can have different dyad members. They live together, they're couples, and they live together. They live in the same neighborhood, but they might have different perceptions on neighborhood safety or neighborhood quality or how well they get along with the neighbors or whatever it is. That's a common fate analysis, actually, right? Because the neighborhood affects both partners equally because they live within the same neighborhood. Right? If you have a child, so think back to the news scale I referenced, the Wee disease. You have a child who has a chronic illness that theoretically affects both partners equally. So that can be a common fate analysis. You ask each partner their perceptions about issues related to their child's disease. That's absolutely a common fate analysis. So I'm gonna walk you because it can get tricky and we can get into the weeds as you've already probably seen. I'm gonna have you all help me think through a couple of different scenarios. So if you're interested in the changes in post-traumatic stress symptoms in couples following an unexpected death of a child, right? So you have a bunch of couples, you have 100 couples, let's say, and they've all experienced the loss of a child. And you want to measure their individual level post-traumatic stress symptoms. My anger, my anxiety, my depressed mood, my flashbacks, my whatever. Can you use a common fate model?
You're looking at the individuals, post-traumatic stress symptoms over time, like that, the common thing. I don't think makes sense.
Okay. What's your rationale?
So, well, so if you're interested in the individual, then predicting because if the common fate is all about a dyad process or a systems level process predicting another systems level process or over time, something like that.
Yep.
You're not looking at the right thing if you're looking at an individual's change or whatever and specific.
Okay. Anyone else have any other thoughts? What if I said what if I changed the questionnaire a little bit? And I said, as a result of the loss of your child in the questionnaire prompt, have you experienced? Does that change anything?
There's kind of this shared concept
Uh-huh.
they're gonna influence each other, but it is such an individual, like it is individual symptoms, individual reactions to it, so that makes me think it's more like.
Okay. Okay. Well, I'm not going to answer the question right now, of course. Right? Let's think about a related scenario. Here's the CESD-10. So you have two partners and they both fill out the CESD-10 and you run a common fate model just because you're curious. And you get these results down here. You want the loadings to be 0.70 or higher. And the loading for the female partner is 0.74 and the loading for male is 0.84. So we have an individual level variable. But when we run it in a common fate kind of modeling technique, we're substantially above the threshold. What do we do? Do we keep it as a common fate and we make a theoretical argument that there's shared depressogenic characteristics within the relationship? Or do we go to an APIM and some of that variation that's going to be shared is now in the residual portion of the models or perhaps coming out in the partner effects? Most likely the residuals, but you'll probably see an increase in the partner effect. What do you do? Because the stats are telling you one thing, but your theory is kind of telling you maybe there's something else.
Maybe it isn't. So my instinct is generally, if the theory says it's not there, but the stat says something is there, remember that statistics is, you know, you put numbers in, and the number generator crunch something together, give you something out. It's like when you're looking at like mod indices, like it'll give you stuff. Sometimes it gives you things that mathematically work, but make no sense.
Okay.
In the real world, because there's some outweigh things we mentioned. So
Okay.
usually if it's a contest between theory and just the numbers coming out the way that I would like, I would at least. In this case, I don't know, this is tricky for me. I'm not totally sure I'm confident in figuring this one out. But kind of as a rule of thumb, I tend to go, if the theory is at odds with what the test is, then I'm at least pretty cautious that the test is saying what I think.
Okay. How about others? What do you do?
I feel like we can make an argument for something bad depression. I don't know if that's the right way to go, but
Okay. So you think that there would be some form of theory that could defend, like, depression doesn't just occur at the individual level, it can occur at the carcinogenic level, or the carcinogenic couple level. Okay.
I think like
Okay. Yep. So yeah, so can we make the argument that there is a depressinogenic process at the couple level? That's really the question here. Can we make that? Are there relationships characterized by depression? This is where your head starts hurting a little bit, right? Can we make the argument that there's something above and beyond the individual that's shared between us that is depression? Or is it that, according to like secondary traumatic stress theory, the depression symptoms are communicable between partners? Is that the process? Is that the reason why they're shared? That's the theoretical argument that we have to make here. All right. So what would I do? So I'll give you, so Jordan, that is with our data, by the way. So we might have to deal with this problem. And so if you use an APIM, you might not be accurately capturing the shared nature of depression. Because I don't know about you, but in my clinical experience, there are a lot of couples who use substances together, and that's the way they bond, is through using. So can substance use even be this relationship level characteristic, right? And I think there's enough of theoretical rationale to say yes, right? So, and I think again, what would end up happening is that variance that's occurring at level 2 with depression or substance use or whatever it is, that's going to increase your partner effects a little bit, but that you're going to see more of it in the residuals, the unexplained variance, because you're not capturing what's shared between partners. You're only doing that to a certain extent of mutual influence. So I think there is a rationale for running a common fate model here. But what makes me deeply uncomfortable is that I'm now kind of skipping a step between theory and measurement, right? Because what I'm doing is I'm inferring that there's a depressinogenic state within that couple relationship without having anything measured at that level. So that's really the part that makes me really uncomfortable with running individual level symptomology and inferring that there's a relationship level process here. And so what I would do is I'd literally run them both. That's what I would do, and let the reader decide. In what I would probably say is that in the common fate discussion, I'll say there is mutual influence. Here's what is happening. And then on the common fate side, then I'll say, alternatively, there might be shared depression, which might be reflective of a theoretical family emotional climate construct that went unmeasured in the study. Further research should do well to develop measures that assess family level symptomology. So I'm kind of inducing or creating the idea of a theoretical framework or referencing something that already exists and saying, I'm going to let you all decide. I'm not going to be put in the middle between reviewer 1 and reviewer 3, yelling back and forth about which way is the right way. I'm going to let the two of you decide. So I think that's how I would approach this example. If we're looking at depression predicting relationship quality or something like that, I would present both models and really let the reader make the decision. To me, it's kind of tapping out a little bit and not, I think there is an argument for not doing that really, really hard thinking that you should probably do. But to me, I think there's equal rationale in both. So that's where I kind of think about, I'll let the reader decide. Because I think if you spend 100 hours thinking about this, you might come to 51%, 49%. One's a little bit more likely than the other. But to me, I think this is actually how you advance research is you pose a discussion section. A good discussion section will pose a new question that can be resolved by future research. Right? And that's kind of what I'm doing here in my approach. Okay, so your common fate variable with 2 latent constructs, you are estimating 13 parameters. You're going to have 1 residual variance. I suppose 1 variance of the exogenous variable, a residual variance of the endogenous, 1 direct path, 2 variances, 2 error variances, 4 intercepts, and 4 error variances for the indicators. So again, this is where we go back to P, the P rule. P plus P times P plus 1 over 2. And when you have just 1 latent construct, 1 common fate latent construct, you are just identifying. And that's why we impose those constraints on the factor loadings, right? Otherwise, you will have negative degrees of freedom. Your model will not run. It's not possible, right? You can potentially get away with that and freely estimate your factor loadings if you are borrowing degrees of freedom from other portions of the model. Let's say you have individual level symptomology and you're using another latent factor. You could theoretically borrow, you just covary them. You can borrow degrees of freedom from other portions of the model, but your local fit, I wish we talked more about this in our SEM classes, local fit will be under-identified always and forever, but your global fit could potentially be fine. All right, so think back to path tracing rules. I have a newfound love, or actually a rediscovered love for path tracing rules and figuring out where I use this in SEM when I figure out when my model's misspecified. And I'm looking in the residual matrix and I'm saying, oh, something's overestimated, something's underestimated. I use path tracing rules. So we're going to apply that to the common fate variable. We're going to go through that real quick. So path tracing rules, just as a refresher, you can trace backwards, you can change direction at a 2-headed arrow, and then you can move forwards, or you can simply go forward. All right. So you can go backwards once, and then you can go around a 2-headed arrow, and then you can go forward, but it's not pictured in this model, but you can't go up here, around here, and then go backward again. Not allowed to do that, right? You cannot go forward then backwards. So once you start going down a 1-headed arrow, you have to stay going down a 1-headed arrow. It's a one-way street, all right? And then you can only have 1 variance or covariance. So let's say there is another factor here and they're correlated. You can't go up around this variance and then bounce over, right? Not allowed to do that. And then you can't go through the same variable twice in any given trace. And then you sum all those path traces up, and that gives you your covariance algebra and gives you your variance explained, right? So in path tracing rules, actually, I'm not going to do that. There's a pictorial representation of that. So how we find out the extent of covariances in the common fate model is we can only do it one way. We go up, so this is backwards. We go around our variance, and then we go back down, and that is the covariance between X1 and X2. So what is the covariance between X1 and X2? Or correlation, I should say. Anyone know? Yeah, that's it, 0.49. 0.70 times the variance of 1, and then back down times 0.70. It gives you a model estimated correlation of 0.49. And so that's generally how we calculate it. It's not necessarily always what happens within an SEM. The model expected, the model implied variances can be a little bit off from that, but generally that's going to be fairly close. And so there are several just matrices that I have memorized. So in OLS least squares, it's x prime x inverse x prime y. That's ordinary least squares regression. And in SEM, it's lambda psi lambda prime plus theta. That is your covariance among your latent factors within SEM. All right. And so again, so what this means is that within a common fate model, 49% of the variance is shared between dyad members. So that's almost half. I think that's pretty good. But if you go down to 0.60, the factor loadings on average, it's going to be 36% of the variance. And if you go to 0.50, it's going to be 25% of the variance. And some people still say a factor loading of 0.40 in confirmatory factor analysis is sufficient. That's so little. That's counting for almost no variance in the outcomes. And if we're really looking at dyad level processes or shared variance and it's really, really low, maybe we're using the wrong model, right? And there's some more formulas. All right, so we'll keep going. So here is, I use the brief example from our co-parenting data. So we have family violence as a reason for divorce, and we have co-parenting. And so what I found is that mother and father's shared reasons for divorce as it relates to family violence. The higher that is, you have a negative 0.12 or 1324 unstandardized unit decrease in the quality of the co-parenting relationship. So the more the dyad agrees that family violence was a reason for divorce, the lower the co-parent relationship quality. Not surprising in any way. The standardized coefficient like negative 0.60 or something to that effect. So an exceptionally strong effect. All right. All right. So let's get into M+. All right. So we're going to use the common fate baseline model. It's actually probably at the bottom. There it is. And we'll use the couples.dat file again. So here we are using relationship mindfulness and dyadic coping, all right? So the first thing that we're going to do is we're going to create our common fate latent variables. So our dyadic coping latent variable and dyadic mindfulness latent variable. And so, as I mentioned before, you have to fix those loadings to 1 in order for statistical identification to occur, even with 2 latent constructs in the model. And so you fix them by using the by statement, which indicates a latent variable, and you indicate each partner's, the male right here and the female right here, and you fix them to 1. Technically, you can fix them to any value, but we're just going to go with 1. That's standard practice. And so that's going to be your, we're having it as our dependent variable. And then we need to do the same thing for our relationship mindfulness for our exogenous predictor. All right. And then we have our regression coefficient. These will be covariances. Right. And then we also need to covary each person's effects, right? So you have the husbands and the wives reports on relationship mindfulness and dyadic coping. So you need to correlate, create a residual covariance between husband's report on construct 1 and husband's report on construct 2, right? And that's what these covariances are within Reporter. And that is it. So we can go ahead and we can run this model. So again, this is the file with 125 couples. So we're good to go there. All of our means, skewness, kurtosis, all of that looks fine. Correlations, covariances, all of that looks fine. And so we go down to our model fit. And so again, with only 1 degree of freedom, your chi-square value is going to be like 2 or less, or it's going to be like 8 or greater. There's not going to be much in between. And same thing with your RMSEA. Your RMSEA is going to either be 0 or it's going to be like 0.80 or a 0.08 and above. All right. So this is one of those models where I just completely disregard the RMSEA. I'll report it because people want it and they're used to it, but I don't give it any type of weight when making a model-based decision. But essentially it gives us pretty good fit. CFI, TLI are all looking good. So we can scroll down to the unstandardized. And so here we see our factor loadings are fixed to 1. And here is our regression coefficient. So a 1 unit increase in dyadic mindfulness leads to a 0.438 unit increase in relation to mindfulness predicts 0.438 increase in unit increase in dyadic mindfulness or dyadic coping, sorry. All right, so that's unstandardized. And we have some covariances here. Even if these are non-significant, I tend to leave them in, honestly, because there's a theoretical rationale for me to leave them in. And if I remove them, let's do that and see what happens. So we'll just keep in mind the 0.438. That's the number we want to keep in mind, and maybe the standard error as well. We can remove these and see kind of what happens. You can just run it again. So our chi-square doesn't decrease, really. I mean, not surprising. We're removing non-significant parameters, so our model is more parsimonious. So that's fine. But look what happened. Our chi-square went up. So essentially what was happening is there was some level of information that is related in those residual terms across partners. And so now that we've removed that covariance from the model, that information has to get out somewhere. And how it's going to get out is through an increase in the standardized factor loadings, but more importantly, that regression coefficient. Right? And so we could be inadvertently artificially inflating our regression coefficients by removing those error covariances. And that leads us to a type 1 error rate. So I leave them in, even if they are non-significant, because I want to be sure that this parameter is exactly what it needs to be. Okay. There might be some, I mean, if you have a theoretical rationale to say they're going to be unrelated, then go for it. Again, it's all based on theory, and that parameter estimate is probably going to be more in line with your theoretical framework. But I have yet to find a theoretical rationale to omit those residual covariances. And so let's look at our factor loadings to make sure that they're above 0.70. And so dyadic coping, we're kind of there. It's not great, nothing to brag about, but it exceeds that threshold. Multiply 0.74 times 0.725. That's the amount of shared variance between them. Relationship mindfulness, we're a little lower. And again, we want to identify general rules and general patterns. We don't want to identify hard and fast rules like the CFI has to be above 0.95. And so here, this tells me only around 35% of the variance is accounted for in males by the dyadic factor. I just square 0.651. So that tells me there's a lot more, there's a little more individual variability here. So that's where we're going to move into a little bit later is let's model that individual variability. So I'm actually okay with this. If they were both 0.65, then I'm starting to feel a little more uncomfortable. If they're both 0.60, I'm feeling a lot more uncomfortable. And so you have to kind of gauge, again, hold your theoretical framework when you're modeling things. To me, this is not a deal breaker. And then you have our standardized regression coefficient, which is, really quite strong, which is not surprising given that they're both communication-based processes. And then we can go to our R squared, and we can, excuse me, we account for 22.3% of the variance in dyadic coping with just one predictor. So that's a huge effect. One predictor is accounting for 22% of all the variation in that. So we have a fairly strong common fate model here. All right. Any questions about modeling just the baseline common fate? Actually, let's actually, I'm going to run this again. Let's take a look at the residuals and things like that to see if we'll look at the latent variable distribution plots and the residuals to see what we might need to do in terms of non-normality. So this ain't great. All right, it's not the worst I've ever seen, but you can kind of see like a really kind of funky curve, but that's not normal. And so we'll go to dyadic coping or dyadic mindfulness. That's a little better, but not much. So to me, you could probably use maximum likelihood here, and we'll actually do that real quick. Let's look at our standard errors. So it's 0.472 and 178. That 472 should not change, or if it does, it'll be very, very minuscule. What we're going to pay attention to is our standard errors. So we'll do maximum likelihood, and then I'm just going to throw a bootstrap on there real quick and see what we get. In terms of our standard errors. So scroll down. So it's about the same. It was, I think, a little bit higher, but all in all, the residuals weren't, all that. The violations weren't really all that bad. And as you move to bigger and bigger samples, that the non-independence of residuals and the normality of residuals becomes less and less important. But we have 125 couples, which is a small sample in dyadic research. So this is like a sensitivity analysis that you might run just to be sure. But I wouldn't even report maximum likelihood because I use robust for pretty much everything. All right, so we can head back to the PowerPoint. So let's put it there. Actually, we're not going to head back to the PowerPoint directly. We're going to head back in M+. We're just going to open up a different file, and we're going to run the common fate model with identical twins. So we're going to do it with indistinguishable dyads. Because we're going to place just a few extra restrictions on the model. So we have CFM indistinguishable as the input file, and we'll use twins.dat for the data file. And if my memory serves me, this model is going to be all sorts of funky, but I want you to just get the coding down, because again, I don't have a whole lot of indistinguishable dyads. So these are a set of identical twins from the MIDAS study, and we are going to be looking at family support and family strain, and we are going to have family strain be predicted by family support. All right. So again, not a great theoretical question, but it's just serving the purposes of getting into M+ and learning how to code the indistinguishable dyads. So you do the exact same thing. You'll do family support by T1 is twin 1, T2 is twin 2, not time. Okay. Oh, yeah, we'll provide an inadmissible solution. Okay. And then, so this first part of the model will look identical to the common fate model that you just programmed in. There will be no differences. The differences come down here, where we are constraining the effect. So you can run an ISAT model before we're diving into the common fate to see if they're indistinguishable. But normally if I'm running a common fate model with indistinguishable dyads, I just jump straight into here and I just impose these constraints rather than running the ISAT model. So you're going to constrain the residual covariances to be equal across partner. So the covariance between person one on construct one and person one on construct two is identical to the covariance on person two on construct one and person two on construct two. Right? Those are going to be constrained to equality. And again, you can name these whatever you want. I try to do like cove or psi so that the labels are actually meaningful. And then the second thing that you're going to do is you're going to constrain the intercepts of the observed indicators to also be equal across dyad members. So the intercepts of those of our support and our strain variables, right? Because we're assuming since they're indistinguishable, they're perfectly the same for our intents and purposes. And so I'm using tau 1 and tau 2. And this should run fairly quickly, so I'm not going to delete that. All right. Any questions about the coding or the syntax? Go ahead and run that. And I'll leave it up here just for another minute to see if anyone's still coding along. All right, so I actually kept some missing data in there so you can see what this warning is. Essentially, if you're running a substantive manuscript, this is a problem. This is where in M+, it listwise deletes if you're missing data on your X values. And so this is where you would throw a FIML line in there. So full information maximum likelihood is accounting for that missingness. And this is where you would include potentially auxiliary variables to account for that missingness. So we have a sample of 382, well, technically it's 398 twin pair, or 398 twins, so 199 twin pairs. But now we have some twin pairs that don't have a partner. Right, so that's not going to pose a huge problem in the estimation. We have some singles in our analysis because we lost some of them up here. All right. All right, so scroll down. So again, this is the warning label or the warning sign that we got. Again, this is not ignorable, but for the purposes of our model, then we're just going to kind of ignore it. And we'll go down and look at our chi-square and our fit statistics. And again, we'll have 4 degrees of freedom. All right. And we have good RMSEA. And so here's just a perfectly good illustration, excuse me, on why the RMSEA with low degrees of freedom is just a terrible indicator. Look at that confidence interval between 0 and 7.9. When you have that close of a fit, that tells me that, I mean, that confidence interval given the model and the sample size is a country mile wide, right? I would expect this with this type of sample size to be 0.40 or 0.04 or 0.03 or something quite a bit lower. All right. And so we'll scroll down to the unstandardized effects. And so what we see here is that for a 1 unit increase in support, there is a 1.175 unit decrease in family strain at the dyad level among identical twins, all right? And again, here's where we want to double check our coding. Are these the same? Sure are. Are these the same? Sure are. And are these the same? These intercepts the same? Sure are. That tells us we coded it correctly, all right? And we can scroll down to the standardized, and we have low loadings here. Again, these are twins that are in middle adulthood. So if these were identical twins and I asked the same family support and strain variables in childhood, these loadings would probably be 0.8 or 0.9, but they might live in different states. They might live in different neighborhoods. They might not be in any type of communication. They might have different relationships with family members. So what this tells me is that, excuse me, we probably want to move to an APIM with these folks. There's just not a whole lot of variation at the dyadic level. It's around 25%, maybe just over 25, and maybe around 32 or 33, somewhere in there. So nothing really all that noteworthy, especially given that they're identical twins. And then we have our latent variable, and this is where our model went awry. So this is where I go to my Tech 4 output to see what actually happened. So that is coding the common fate model with indistinguishable dyads. And my argument is you should be testing this even with theoretically distinguishable dyads just to see whether or not you're harming your model data set. So essentially, this is the ISAT version for the common fate model. All right. So that is, any questions about the coding, about the interpretation, or anything like that in relation to the indistinguishable dyads within the common fate? Okay. So now we will go back to the PowerPoint, and now we're going to step it up to mediation. And this should take us to lunch, and then in the afternoon, we have moderation, which will take a little bit longer because we're going to talk about some really cool stuff. And it looks like we're actually going to have some extra time for that in that second afternoon session. So we can go over whatever other dyadic models you all want. So that's what it looks like. All right. So, whoops. Come on. All right. So, like the APIM, we can extend mediation to the dyadic level. We can test indirect effects through from one dyad level variable to a dependent variable at the dyad level through a third intervening mediating variable that also occurs at the dyadic level. All right. So essentially, this is in other words, it connects dyad level processes to one another via mediation. So essentially, this again goes back to the idea of how we do things and how this process affects us. Right? So I'm going to talk a little bit more about assumptions of mediation, since I didn't talk about that with the APIM with mediation. One is there is a mediating process occurring, and it occurs at the dyad level. And I think when we just think about it statistically, that makes a lot of sense. It's pretty straightforward. It's probably not overly complex and not well beyond your first year grad stats that you've probably taken. But let's think about it conceptually. What would dyadic mediation look like? So we have like family satisfaction, family emotional climate, we have family communication. Do we think that there's indirect effects at these kind of higher order levels within our model? And that's where I've been doing these analyses for a little while now, and that still makes my head hurt a little bit about how do I really understand mediation at that dyadic level, at that shared level. All right. How is that digesting in you all? Is it landing easily, mediation at that second level, or what does that actually mean? So if I said family violence is associated with lower quality co-parenting relationship, which is associated with greater child behavioral disturbances in relation to following divorce. Can you conceptualize that at the dyadic level, at that second level, that relationship level?
So just trying to show the mediating construct. So independent, dependent, and mediating constructs are all at the dyadic level in this case.
Correct. Correct. Yep, your independent, mediating, and dependent variables are all common fate latent variables. So it would essentially mean shared reasons for divorce would predict shared perceptions of co-parenting relationship quality, which would predict shared child behavioral problems following separation. Does that make sense, or is that a little bit of a, what does that actually mean? What does that actually look like in practice? Because I'm a clinician, I try to translate everything I'm doing into how would I implement this with my clients. So is that making sense? Yes, no?
Mostly,
Okay.
it hurts my head to distinguish just the whole concept of system level processes.
Mhm.
You can always get kind of sticky when you're trying to distinguish true systems level things as distinguished from I influence you influence me,
Yes.
like the whole time. You need
Yeah.
both to really get a system, and that's always a hard part of systems theory in general. It's trying to understand what those system level processes are that you don't capture by individual.
That's exactly right. Yep. So yeah, so I think that, I mean, if that's where you're at, then that's probably where you're supposed to be, to wrestle around with these things. And what we'll probably find is that we can actually have variables like relationship quality that, actually, relationship quality is probably not a great example. You can have variables that you model as a common fate variable, but when you think about it theoretically, it doesn't actually doesn't make a whole lot of sense, right? And so just because you have a dyadic measure doesn't necessarily mean you have to use a common fate variable, and doesn't mean that you have to test mediation. Okay. So that's the first mediation. That's where I want a lot of us to do that critical thinking is there really a dyadic process going on? And is that related to another dyadic process, or is it related to an individual process, right? I could have trait levels of anger, which affects our shared communication processes, and my partner can have that too. So it might be that you have a common fate variable predicting an individual outcome or being predicted by an individual outcome. Observed indicators for both dyad numbers are reliable. Again, this is where we are cupping our ears saying la 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 in terms of measurement error, right? You want to test invariance here. Across dyad members, you want to be sure that that omega or alpha or coefficient H or whatever you use, that they're roughly the same. And that's actually a simulation study that I'm beginning to work on and think through is what are the implications of, let's say you have the wife, the Cronbach's alpha is 0.70, but the husband's is 0.85. How does that impact the parameter estimates? How does that impact that regression coefficient if you have differential reliability across dyad member? Mm-hmm. And then the dyads are affected by a common cause, right? And of course, the assumptions of SEM must be upheld. So here's your common fate mediational model. Again, probably not a big step from the baseline common fate model. We're just adding in another perhaps dependent variable, and then we're adding in perhaps, based on your theory, another gamma. So the research questions, excuse me, do couples levels of dyadic coping mediate the relationship between couple communication and marital satisfaction, right? Does dyadic communication mediate the relationship between family chaos, right? You can go family level, and dyadic closeness in parent-adolescent relationships, right? So we probably, and again, these research questions that I'm kind of proposing, they don't look a whole lot different from what we already write, which to me is the problem, right? If I can write a dyadic level in an individual level research question using the exact same freaking words, then what is my theory telling me? What is my introduction telling me? And what am I actually arguing here? And that's the reason why we have a huge replication crisis. I think that's a contributing factor. All right. So this is the exact same thing as the baseline common fate. We're just adding another construct. So you're just fixing those factor loadings to be 1, and then you're estimating those extra regression coefficients, and then you're adding those covariances. Right? That's it. That's the only difference. And then if you have indistinguishable dyads, you're fixing those covariances to be equal, and you're fixing those means to be equal. That's it. So if you can run a common fate model, you can run a common fate mediational model really easily, right? Here is a common fate model that should not be a common fate model. You have, this is among twins, I believe. So you have SES. Okay, I could see perceptions of socioeconomic status being a common fate variable among twins. Sure. Personal growth? No. Nope. You lost me. All right. So personal growth is not a dyadic level construct in any way, shape, and form. It's in the name, personal growth. Attitudes towards education? I mean, depends on the measure, honestly. If it's my individual attitudes towards education, then sure. Or then no. If it's family level, we as a family value education, then go for it. Absolutely. But I would say, even if the measures of personal growth, we as a family value personal growth, I mean, maybe, but I don't know why you'd ask that question, honestly. Like, I don't know, it feels a little off to me. This is to me, a not so great example of a common fate mediational model. So I'm going to walk you through a paper I've had under review for like 9 months now. Thank you, JMFT, for their special issue in co-parenting families. And this is a common fate mediational model. And I think I probably argued the hybrid model. We can talk about why there's a distinction there. But essentially, it looked at reasons for divorce, including raising children, differences in raising children and differences in parenting and family violence. And that's predicting co-parenting and children's emotional and conduct problems, all reported by the mothers and the fathers. Pay no attention to the directionality of the arrows. They are backwards. I actually wrote this as an emergent latent construct. So the arrows on the indicators should be going the opposite way. All right. This was not estimated as a formative latent construct. All right. And so, good Lord. So what we have here is the more the couple, I don't want to say agree because that's the incorrect interpretation. The higher the levels of the couple at the couple level of raising children being a reason for divorce, it was associated with a decrease in the couple level of co-parenting, and reasons for divorce in terms of raising children differently also predicted directly conduct problems. So the more the lower the parents were in differences in raising children, the fewer conduct problems there were. But the higher and higher and higher the couple got, the more and more conduct problems that existed. Right? And these are unstandardized effects. Right? These are unstandardized. And then we have IPV demonstrating those same effects. And what we didn't do in the first round, which I'm going to do in the second round, is we can constrain IPV and raising to be equal. See if that negative 0.25 and that negative 0.40, to see if those are significantly different from one another. Because if they're significantly different from one another, that gives us a brand new piece of information. Likewise, we can constrain these to be equal, and we can constrain the indirect effects of from reasons for divorce on child behavioral problems to be to be consistent. All right. All right, so let's go back into M plus. All right, so we are gonna, again, same data file. So couples.dat, and then the input is common fate mediation. And I don't know why I exited out. There we go. All right, so here you're going to see that I'm just using straight up ML with some bootstrapping. And actually, you know what? I'm going to let you all code the syntax on your own without any guidance, because you should know how to do that now. And we'll see how correctly and you all get. Let's so dyadic coping, relationship mindfulness, and relationship satisfaction. And then you will have dyadic coping as your mediator between relationship mindfulness and couple satisfaction. So you're not using the CESD variables, you're using the other six. So relationship mindfulness, dyadic coping, relationship quality. MNF, correct. Yep. And don't forget that model indirect command that we talked about yesterday with the APIM mediation model. And these are distinguishable. I think you're probably going in assuming that, but I just want to clarify. These are distinguishable. All right, then I will pull up my syntax and right. So what we have here is we have our first common fate construct, latent variable. We have our second with everything fixed to 1 in both of them, and our third. And the order here does not matter. So if you have them in different orders, doesn't matter. And then we have our dependent variable and our mediator predicting our independent variable, our exogenous variable. And then we have, oops, that looks like this is backwards on an RMF or dyad. All right. And then we have our covariances between all the mail reports. with one another. This is kind of a shortcut. Rather than specifying them individually, you can just type them all out and then have a with statement and then type them all out again. And then you do the same thing for the female. And then here is your model indirect command. So your dependent variable, IND, your independent variable. And then don't worry about everything else. And then the sample, the output I gave you should be sufficient. All right. So we can go ahead and run this. I bootstrapped it, so don't feel the need to if you don't want to. So scroll down. So we have 3 degrees of freedom. Our chi-square is 11.54. Our CFI is 0.95, which is good. Our TLI is kind of yucky. So chi-square is giving me some hesitation. RMSEA is quite high. Again, low degrees of freedom, so I'm not placing a whole lot of weight onto it, but in combination with a chi-square and a TLI, I'm beginning to wonder about model data fit, so I'm going to go poke around in the residual matrix at some point. Then we can scroll down, make sure all of our factor loadings are done properly. And we have our direct effects and our indirect effects, or our direct effects here. And so what we have is, where'd my other on statement go? Hold on. Maybe that was correct. So that was correct. I had it right before. That was our direct effect. Then we have our direct effect here. Where did you go? Undyad mind, there it is. And so we don't have mediation here. So as you can see, this is non-significant. This is non-significant. This one is significant. But one of the things that I'm thinking about is, actually, let's scroll down to standardized to before I give away the answer. We don't, according to our unstandardized results, we don't have any mediation. So take a look at that. Let's scroll down to our standardized. Those p-values are all significant now. So when in our unstandardized results, only one of those paths is significant, but in our standardized results, all of those p-values are significant. So when this happens, I always trust the unstandardized more than the standardized. All right. I trust the unstandardized effects. That tends to be what I report. I'll report standardized coefficients, but I will use the p-values of the unstandardized effects if there are discrepancies like this. But what I think is happening is look at those standard errors. Look at how high they are. Because when I think about standardized effect, this is a huge effect size, right? 346, 432. Those are big effect sizes. And so I believe that they're correct. We probably don't have, probably have a lot of sampling variability. We don't have a whole lot of precision in our estimates. That's what our standard error is telling us. And so my view is if we collect more data, and that's not the answer to every reason you don't get statistical significance, but given that we have these pretty large effect sizes, if we just add people, then we're probably going to find something significant. Or perhaps it's due to our sampling method. That could be an absolute reason why we have so much variability in this as well. So again, we'll need to think on why that's happening, right? But essentially, this is these are our results, and I report unstandardized over standardized, right? But let's try it with MLR and see if we get different results.
So we'll scroll down. We'll go back down to our, we'll go up to our standardized first. Now look what's happening. Now everything's statistically significant. So these p-values before, they were 0.11, 0.12, 0.10, somewhere in there. But when we added in that scaling correction factor to account for non-normality in our residuals, we ended up being fine. So this is, to me, this is why I use robust maximum likelihood almost 100% of the time now. I argue it should be the default rather than maximum likelihood and bootstrapping. Because if we go and look at our, let's look at our histograms of the residuals for each of them. We'll go in order. So dyadic coping, nothing to brag about, not horrible, but clearly not normal. Probably won't mess up your results all that much. RMM's your independent variable, so I'm not really worried about all that. Dyadic coping female, ain't too bad, right? I would feel comfortable using maximum likelihood under these conditions for the most part. I wouldn't balk at that. And then you have RMM for the female, and not great, but it's clearly not the worst thing I've ever seen. Again, not great. There it is. There it is. This is what the scaling correction factor allows us to adjust for. It's the residuals on the female and relationship quality. And again, you would come to a completely different conclusion in your model if you based on robust maximum likelihood versus bootstrapping. All right. All right. So actually, let's actually, are there any questions? Any questions about mediation at the within the common fate model? Let's go to lunch 10 minutes early. I know it's been these are heavy mornings, so we can we'll go to lunch early, and then we'll still come back at the same 1 o'clock, and then we'll probably quickly move into parsing out individual and dyadic parameters, and then we'll move into the moderation within the common fate model with LMS, right? So have a good lunch, everyone, and see you back here at 1 p.m. Central.